that all right? All right. So, my name is Frank Wilczek. This is an experiment in presenting material that's for graduate students, but yet supposed to be open-ended, suggesting research topics at the frontiers of physics. Please ask questions as they arise. There'll be one lecture today. This is, I'll be talking about Koopman von Neumann mechanics. If you don't know what that is now, you will in an hour or so. And then next week, I'll be giving 2 lectures on each of 2 topics. One about the quantitative aspects of unification, and another series of 2 on quantum search algorithms. Okay. In both of those, we'll reach frontiers of physics in a couple of lectures. Okay, so what is Koopman von Neumann mechanics about? Well, we usually formulate quantum theory and classical mechanics as if these are 2 different universes. In classical mechanics, you don't have notions like Hilbert space, operators, wave functions, all these dominant concepts of quantum theory. And that's kind of disappointing. One would like to think that quantum theory is the more basic theory and should contain classical mechanics as a special case, and one should be able to incorporate classical mechanics within the same framework as quantum mechanics. Also, as we'll see, this has not just conceptual interest from the point of view of philosophy, but will enable us to formulate new kinds of theories that combine classical and quantum theories in interesting ways that haven't been fully explored. The formulation of classical mechanics in language that's reminiscent of quantum mechanics, that is, that does involve Hilbert space, operators, and wave functions, was achieved by Koopman and von Neumann in a series of papers in the early 1930s. They used it as a technical device. Von Neumann, in particular, used it to prove ergodic theorems using Hilbert space methods, ergodic theorems of classical mechanics using Hilbert space techniques, and it's also been used as a technical device to formulate semi-classical approximations to quantum mechanics. But I want to consider it from a more fundamental, from the point of view of possibly doing something more fundamental with it. Okay, so let's get down to business. The formulation of classical mechanics that lends itself to modification so that we get it to look like quantum mechanics is the formulation using density functions in phase space. You're probably familiar with this sort of thing in treatments of statistical mechanics, where you write distributions of probabilities for many copies of an individual system. This is the Gibbs procedure. And have a density in phase space representing their the probability that in your distribution, or the density of copies of your system that you have with a given value of x and p. And of course, this can also evolve in time. So that sort of looks like a wave function, but involves two, it involves x and p, but if we're doing classical mechanics, we should expect a wave function to involve both x and p, since x and p commute with each other. If we want a complete set of commuting observables, we will have both x and p. But what's more disturbing is that this rho is necessarily positive semi-definite, because it's a density of systems, density of the number of systems, so that it doesn't support any kind of superposition principle, and so it doesn't look like a quantum mechanical wave function. The space of possible densities is not a vector space. It doesn't form, much less a Hilbert space. So the beginning thought is to pass from rho to a wave function such that rho is the absolute square of the wave function. Sliced. Like that. Then the probability distribution, the distribution of systems, of our system in phase space, then rho, which in statistical mechanics treated the Gibbs way, would be interpreted as a probability of finding your system with position x and momentum p, would be given as like a probability in quantum mechanics. I should mention, by the way, that I'm going to use notation, as long as I can get away with it, as if we have a system with just one degree of freedom, just to keep things simple. Okay, but of course, but this is not the end of the story. This is just the very beginning. We need an equation for psi to encode its dynamics, and we have to have something that looks like a quantum mechanical Schrödinger equation and is implemented by appropriate operators. So let's remind ourselves what the equation that rho satisfies is, and then how we can use it to guess an equation for psi. The equation that rho satisfies, famously, is nothing but the continuity equation, or conservation of probability, or also called Liouville's theorem, which says that if you regard rho as a fluid in phase space, it's incompressible. So this is Liouville's theorem. It says that the total derivative of rho with respect to time is 0. And that's equal to still a little jet lagged, so you'll have to make allowances. The partial derivative with respect to time and the convective derivatives in the two directions. Of space, which is phase space, so the two directions are x and p. Okay, which can also be written as d rho by dt equals minus x dot d rho by dx minus p dot d rho by dp, or taking advantage of the Hamilton equations, minus dh by dp and plus dh by dx. And that sort of looks like a Schrödinger equation. We have an equation that's linear in time derivatives. And the inspiration of Koopman and von Neumann was to suppose, or postulate, I guess, that we have a wave function, psi of x and p, that satisfies the same equation. Then, because the derivatives are linear, the differential operator that acts on rho is first order in x and p and t. That if you have a psi that satisfies this equation, then psi star psi will satisfy the same equation. Just by applying the rule for differentiating products, the Leibniz rule. So that means if we postulate a psi that satisfies this equation and interpret its square as a density in phase space, then it will satisfy the correct equation for a density in phase space. We can make it look even more like the Schrodinger equation. So we have d psi by dt equals minus dH by dP. And we can make it look even more like a Schrodinger equation by multiplying by I. Yes, it looks like that too. So that's a promising start, but we really want to go a step further. We want the evolution psi of the wave function to be given by a unitary evolution. That is, we want psi of x, p, and t to be governed by a unitary series of operators from x, p, and 0. Where the u's, of course, satisfy the rules of multiplication. U of t1 plus t2 is the product of u of t1 times u of t2. And when I say unitary, it means there's some inner product we want to preserve, and the inner product, of course, is just the inner product with the norm is integration over space with a fixed value of time. Or I should say, we can go from an inner product from a norm to an inner product in the usual way. We only have to talk about the norm, and that's going to be the absolute square with the measure dx dp. Now, there's a theorem which is a general theorem about Hilbert spaces and how you represent one-parameter groups like this time evolution that tells us how the wave function evolves in time, one-parameter groups of unitary transformations, called Stone's theorem, which is important in the foundations of quantum mechanics. For physicists, it's second nature, but it's less automatic in this framework, so it's important to single it out. Stone's theorem says that if you have a situation like this, with a one-parameter group of unitary transformations, then there has to be an operator, a unitary operator L, call it the Liouvillean operator L hat, and I'll always put hats over operators from now on. There has to be an operator L hat such that the derivative of the wave function is that operator acting on the wave function. And we put an I in there so that this L hat is Hermitian. In familiar quantum mechanics, L hat turns out to be the Hamiltonian, but in Koopman von Neumann classical mechanics, that's where the crucial difference is. We'll find that L hat is not the classical Hamiltonian, but something we have to work a bit to determine. Okay, am I okay so far? Yes.
Do you mean that the integrate is equals to some constants?
It's in
The second.
that this is independent of time. That's what it means for the norm to be preserved under this kind of evolution.
So this
Yeah.
gives a way to introduce the Planck constant?
Well, we're going to do in classical mechanics. We're not going to have Planck's constant, but we'll have Hilbert space operators and everything. No Planck's constant. You'll see. Okay, we want. I should backtrack a little bit. We want to have our dynamical variables and also represented as, and observables represented as operators to complete the parallel between classical mechanics and formulated this way and quantum mechanics. In quantum mechanics, we have operators that implement observables. So we want to have operators X and P that implement observables. And in this wave function representation, these are simply multiplication. That is x hat of psi and xp equals x, psi of x and p, and I can put in time as well, and p and they commute because they're both multiplication operators. Right. But in classical mechanics, we want these to commute, and so we can implement them both as we can take simultaneous eigenvectors of both of them and set up a representation of wave functions so that they're both represented just as multiplication. Okay. In the notes, I started from more primitive axioms, not assuming a wave function, but kind of deriving a wave function by this kind of argument about simultaneously diagonalizing commuting operators. But in order to compress things, the discussion, I'm going to assume that the steps that lead to the wave function are more or less routine, and I won't return, and just say that you can simultaneously diagonalize. If x and p commute, which is what we're going to be assuming for classical mechanics, this is where classical mechanics does not equal quantum mechanics, then our wave functions can be simultaneously eigenvalues of x and p. X and p will be a complete set of commuting observables, and so our wave functions should be functions of both of those, and the two of them are represented as multiplication. Because we've simultaneously diagonalized both of them and written the wave function in that basis. Okay, so now when we turn to dynamics, we get into an interesting conundrum. We would like to implement the correspondence principle which says, and now for simplicity, I'm going to specialize to the case of particle mechanics, particle Newtonian mechanics, but the arguments you'll see will be clearly generalizable. We want to ensure that we have for the dynamical variables that we reproduce in expectation values Newton's equations of motion. So that's the correspondence principle, that we reproduce Newton's equations of motion for the dynamical variables of our system. So, I mean, in quantum mechanics, it's kind of a guiding principle. In classical mechanics, if we think we know that this has to be true, then we definitely can invoke it as a guiding principle. That so it's not. We're just. So in classical mechanics, it's almost a definition. We want the Newton's equations of motion to emerge from our formalism, and so we must demand that the derivative of the position is momentum divided by mass, or velocity, and the derivative of the momentum expectation value is the force, or minus the derivative of the potential. Okay, and now this hat notation will come in very handy as we go to more advanced considerations. This hat notation means, when I put it over the whole thing, I treat this expression as a function of x, as if x is a number, until the very end, when I turn all the numbers into operators. Well, it's not important at this point, but it will be important later. You'll see.
So the hat always means multiplication operator.
What?
The hat means multiplication.
No, the hat means just turn whatever is in here into operators. In this representation, the operators are multiplication, but we'll want to consider more general things shortly. What's that?
Is there a unique procedure how to turn anything that's under the hat into an operator?
Yeah, I mean, it's just if, okay, so if this is x squared, you turn it into x hat squared. If it's x cubed, into x hat cubed, and so. So this is some function of x, and so as long as all the operators commute, it's pretty clear that you just put hats over them in order, and you're not doing much. But
And
in
then like x1, x2,
yeah,
non-commuted,
then
then
it's
some ambiguity.
right, or if right.
But then it,
Or if you were working in some other representation where x was not just represented as multiplication, it wouldn't be so clear what to do. But the procedure is you treat x as a number in here until the very end and then turn it into the operator.
fair to say that then it means that you take the function u prime of x, and then you turn it into the multiplication operator. Right?
Yes. Well, in this representation, when we've diagonalized x and p. In other representations, it might be much less clear. So, but whatever this is a representation independent procedure. Okay, I guess that's the right way to say it. And it may seem like a fussy point here, but it's one of our most important formulas will rely crucially on being able to do this, as you'll see. Yes.
What's the relation between this group and the unitary evolution?
No relation. It's just the same letter. No, I'm sorry. Well, as you may know, physics notation is not entirely unambiguous. So people use the same letter for unitary operators and for potentials, and well, I think these are sufficiently distant in concept space. I don't think there's much danger of confusion. But yes, you're right. This U has nothing whatsoever to do with the unitary evolution. So, yeah.
By expectation value, you specifically mean some kind of average with the density?
Yeah, there's a wave function, and for any wave function, this has to be true. Okay. And that's not trivial. Well,
Is it true for classical mechanics? Is it true for any distribution function?
here we go. Oh, well, watch, and then ask again in a couple of minutes if you still. Okay, so that's the equation we want to get. Let's write out the first one, for instance.
Frank, you asked a question.
Yeah.
Suppose I follow your logic. So is that, I just want to try to understand how this equation comes out when you have a dynamic equation in terms of L.
Yeah, that's what we're going to do.
So,
Ask your question again
okay.
in 2 minutes if it's yeah. No, this is the absolutely crucial. I'm amazed it's taken so long to get here, but okay, this is where where the rubber hits the road. So we want to ensure that d by dt, and let me write the wave function now more abstractly as a function of t, x hat psi of t, so not assuming that we've diagonalized x and p necessarily, but we could have. This is equal to, because we have the master dynamical equation, now writing psi of t. This Schrodinger equation. Okay. We have the derivative acting on this term or acting on that term. Acting on this term, it gives an IL. Acting on this term, because it's the ket vector, it's the complex conjugate, we get minus I times L. And the upshot is that this becomes minus I times psi of t, the commutator of L with x. except everything's okay, except it's a plus sign. Figure it out. One is correct and the other is incorrect. I think this is correct.
I guess that's part of the definition of L.
Well, we're using this equation. Let's see if we got it right, actually.
Right.
So it's like this. So if the dB dt acts on here, it has a minus sign, minus I, which is what we get here. So if L is acting on this guy, we get a minus I. If L is acting on that guy. It comes from the complex conjugation of this. To get the ket vector, we get a plus and L acting on the other side. Okay, so very simple algebra gives us this. But we want the correspondence principle to hold for any psi, so we can infer that we want the equation d by dt of the operator x equals I times the commutator of L with x. Okay. Which is just the sort of thing you meet in quantum mechanics, where L is the Hamiltonian, and you get dynamical equations for any variable by commuting with the operator Hamiltonian. But here we're in trouble. If we try to construct L out of x and p, we're just going to get 0. Okay, Stone's theorem says there has to be such an L, but it doesn't tell us that it can be expressed in terms of x and p. We may need other operators to implement it. And in fact, we do, because there's no way to get a non-zero result. The p over m we want for the correspondence principle from vanishing commutators. We just get 0 no matter what function of x and p L is. So, the solution to this is to postulate, and we can also, we'll later prove that this postulate is correct. But let's for the moment just take it as a hypothesis that we can have operators that are conjugate to x and p, so that do obey non-trivial commutators.
That makes it the derivatives, right? Not the
Yes, they will. Yeah, will come. Yes, very good. You're anticipating these in the representation. So, in the representation where x is multiplication by x, lambda x would simply be minus I d by dx. Okay, and so in the basis where x and p are diagonal, we can represent these as simply derivatives, which proves they exist. Okay, they'll exist in any representation, but in the representation where we diagonalize x and p, so they're realized by multiplication, these are simply derivatives with appropriate factors of I. Okay, and we assume that all other commutators are 0. So between xp, lambda x, and lambda p, all the other ones are 0. Which is true, of course, if we use these differential operators. Now, in terms of those operators, we can construct L. We can and in fact, I'll just write it down. Like that. Okay, now if we take this first term and put it in here, we'll get exactly the commutator we want. The second term will give us nothing, because x and lambda p both commute with x. So we reproduce this one, this equation of motion, and you can verify, I won't go through the algebra, that using this term, we get the correspondence equation for the derivative of the momentum.
So in a way, they are putting each bar to 0, to 1, because the momentum that in quantum mechanics has xp, I
Yeah.
h bar, is now minus I ddx.
You
So
could-
with an h bar xp, right?
Well, yes, but this is not, well, you could put any number you want
Sure,
there.
Sure, sure.
But the point is, this is not the momentum anymore.
Yes, I know.
This is nothing, this is a new element that has,
But it
is
becomes as if I would be using the quantum mechanics relation and put h bar to 1,
if it were the momentum,
if it would be.
then you could,
Exactly.
right. Well, we'll come back to a thought like that momentarily, but yes. It's like putting h bar equal to 1
Yeah.
or 6,000 or some number, in any case, not a physical constant. It's completely conventional,
Yeah.
but not 0.
But not 0, yeah, definitely.
So if you somehow integrate out E, can you get something like quantum mechanics where lambda x corresponds to momentum? No?
I'll show you how to, I'll answer that question sort of indirectly as we go on. But if I don't, please ask it again. Okay. Now, a very profound and important point here is that we have two classes of observables. We have our original classical observables, x and p, and any functions that can be formed out of them. Those would be the normal dynamical variables you'd have in describing a classical mechanical system. If you know its position and momentum, you know all there is to it. If you have a distribution in phase space, that's all there is to it. You have to know the densities as a function of x and p. But now we also have things like lambda x and lambda p, which represent, in the basis when x and p are diagonal, derivatives with respect to x and derivatives with respect to p, but in any case are not functions of the operators x and p. These are not classical observables. In fact, let's go back to the beginning. We went from the classical formulation of densities to wave functions by taking a square root. But taking a square root is ambiguous. We don't get a unique wave function from a distribution. Okay? So there's more information, if you like, in the wave function than there was in the distribution. The wave function has non-classical stuff beyond what the classical theory contains. It may or may not be physically meaningful, but it's certainly not contained in the classical theory. We can express this as a gauge symmetry which says that the classical observables are invariant, they can't change, if we multiply our wave functions by a phase which depends on x and p. An arbitrary phase that depends on x and p always cancels in this absolute square, so it can't affect any classical observable, since this was supposed to be the whole representation of the classical system. But it does affect the value of these derivatives. Derivatives like dx by dp or dx, or d by dx or d by dp. Okay, so if this is a non-trivial phase, it will leave all classical observables invariant, but not the wave function. And observables you construct, that is, Hermitian operators you construct that do change under this transformation, like lambda x and lambda p, represent aspects of the formulation of classical mechanics that have been introduced by passing from densities to wave functions. They're not part of the original classical mechanics. So we have classical mechanics represented, but only in the gauge invariant sector. The not gauge invariant sector is going beyond the original classical theory.
So in order to restore full quantum mechanics, then you have to go to the point to say Lx is h bar times p.
This is not quantum mechanics. This is classical mechanics. This is this is classical mechanics. If you restrict to the gauge invariant sector, where the gauge transformations are this, then it's classical mechanics. Full stop. There's no way, of course, full stop. It's not a quantum mechanical system. It's a classical mechanical system.
But I just to get the gain of that.
Yes.
I thought naively that now you have a framework that sort of is very similar.
Very
It's
similar,
mechanics,
right.
So it must be very easy to immediately see what do you leave in quantum mechanics to arrive there. It must be simple than what we're usually used to, right?
One would be tempted to think that if you take a quantum mechanical system and set h bar to 0,
But that's not quite it, right?
Well, that's overly simple. There are ways of constructing semi-classical approximations using this framework that are quite interesting, but I'm not going to describe them today. They require more work to develop. My attitude is actually quite different. I think that the really interesting possibility here is to formulate theories that are neither classical nor quantum mechanical, but a mixture of the two. Let me backtrack a little bit to present.
So I guess.
Well,
I think I'm just
Look-
question is like they try to map it's like new framework, right?
yes.
So it seems to me suppose you want to get the quantum limit. So
There's no quantum limit of a
Yes.
classical system.
no,
There could be a classical limit of a quantum system.
Okay, not the quantum limit. It's more like the quick way to not the real. It's more like you start with a classical theory. People start with the Poisson bracket.
Yes.
You replace that by basically it's postulate. That's what.
Yes.
So you say, okay, make a postulate that you replace this classical Poisson bracket with the direct, this commutative bracket. Then you get your quantum mechanical description right away, right? So that's like more like it's a map.
Well, I would say
Here it looks like I guess Andrews was asking, would this new formalism provide the easy way to map your classical theory to quantum mechanical theory and vice versa? Because in the old-fashioned way, you start with the equation, you replace the Poisson bracket.
I would rather say that it just
Then you jump
allows.
to the end right away, right?
Okay,
That's how you-
if you're given a Hamiltonian
Uh-huh.
or given a classical system, in the conventional way, when you quantize it, it looks like it's in a whole different universe than the original system. It's suddenly in Hilbert space. It suddenly has operators and so. In this formalism, the classical theory already has a Hilbert space and operators. So it lives in the same conceptual universe. That allows possibilities of joining quantum mechanics and classical mechanics that didn't exist otherwise. Let me put it another way, and then I'll come to your question, which is really when we pass from a classical system to a quantum mechanical system, the key assumption is always assuming xp equals minus I times h bar. But I'll put h bar equal to 1. Or I guess, in this order. And if you have many variables, so if you're dealing with a many variable system, you postulate xi pj equals, well, let me not use I then, j k equals I times Kronecker delta of j and k. But suppose, and that's a very successful assumption with many important applications, but it seems like kind of a very special assumption. Suppose we loosened it up a bit to assume only that xi, xj, pk is some anti-symmetric set of numbers, ajk. And or set of well, I'm sorry. Let's not divide the thing even into x and p's, but suppose we just have a bunch of variables. Let me call them yj and yk with an anti-symmetric form on the right-hand side. Right, it's an anti-symmetric form of numbers. That's more general, might seem like a more general natural framework than assuming we have just one number. And so. But the point is that there's a canonical form that tells you, a standard theorem in linear algebra, that tells you if you make linear transformations among these y's and rescale them in the appropriate way, then this apparently more general form reduces to this one almost. It actually doesn't. What you get is some set of x's and p's that all have the same kind of commutator, like that. So you divide your variables into two pieces, but then you may have some leftover y's that commute. And I'm assuming all the cross commutators also vanish in this canonical form. So this big matrix of A's can be simplified to something with just ones and minus ones along the diagonal. Whole bunch of blocks like that, which we call the x's and the p's, plus a bunch of zeros. So in this more general framework, it's very natural to think that you have some quantum variables and some variables that you would treat as classical variables, some variables that would fall into the Koopman von Neumann framework. So that's the underlying thought and motivation, is could the world contain that kind of structure? What would it look like? What?
A set of variables, some of the quantum mechanics,
Yes.
in the sense they are not commuting.
Yes.
And another set they are commuting with the rest.
Yes. So for instance, it's well known that if you try to quantize gravity in general relativity, it's kind of outside the spirit of general relativity to apply the quantum conditions. Maybe you shouldn't. Maybe you should treat the variables as classical. Now, it's thought that that runs into inconsistencies, basically because the classical theory and the quantum theory live in different worlds.
So,
but they don't live in different worlds if you formulate it right. Yes. Yes.
So the idea is you can use wave function to actually describe the classical.
You can use the whole wave function, Hilbert space, operator apparatus of quantum mechanics to describe the classical theory. Right. And the classical theory is contained in the gauge invariant sector with this special gauge symmetry of that sort of Hilbert space formulation. So classical mechanics in this framework, you might say, is the gauge invariant sector of quantum theory.
But then the classical variable and the quantum variables may couple through the gauge field.
Yes. Yeah. Well, we'll come to that. Right. Yeah. Now, then it gets interesting. Right. Yeah. Yeah.
So if you, on the contrary, if you start from quantum mechanics, like quantum integral formulas, or I know there's this approach with quantum mechanics in phase space, can you get like can you give meaning to this psi of x?
You can formulate all this in path integral language.
Well, I mean,
it's complicated. Well,
if you start with path integral when you take the classical limit, and can you somehow recover this psi of x?
The answer is yes, and you can formulate a path integral formulation of quantum mechanics, of classical mechanics, that looks very much like the path integral formulation of classical mechanics, of quantum mechanics. And in fact, I can indicate to you how to do it. Let's do that.
So you want to take a break, or you want to finish in one shot?
How are we doing?
You decide.
Let's.
So how long is the whole lecture?
I can make the main point in less than a half an hour, I think.
Okay.
But I'll let, yes, depending on how many questions there are, of course.
One more small question. Like
Yes.
your argument, starting up from the y, j, yk,
Yes.
and going to the representation down there, the y's that stay left over, do they commute necessarily with x and p? Or
Yes.
don't they? They do.
Yes. I shouldn't have called them Ys because they're transformed versions of these
So y prime,
Zs.
so basically y
Yeah.
contains x and p and the rest.
These are the X's and P's and Z's are linear combinations of the original Ys.
Fine,
Yeah.
So y is like completely set.
But then you have additional equations telling us that z's.
The Z's commute with the X and P's. These are the only non-vanishing commutators, right? So the commutation matrix looks like this thing with zeros everywhere else.
So Frank, maybe I would propose you pause and take questions.
Yeah, I'm taking questions.
Then you take a break and start the next half an hour.
Or do you want to carry it over till Monday? Maybe that makes the best sense because, look, I've thrown a lot at you already, and it's a little bit abstract, well, a lot abstract. And I have notes that are very eloquent, very coherent. I could have these distributed. People could look at those, and then we could resume on Monday when it really gets with the stuff that really gets interesting, and in half an hour or 45 minutes plus questions, we could start to explore that.
Would that delay your next lectures? You have the three lectures, right? So you want to combine? So does that mean you create a new lecture?
Vincent, like here, we are not yet tired.
You're not
Tired.
So we should continue then.
I think so.
Okay, let's continue then. That makes sense. Okay, but anyway, I do want to I want to make sure that everyone has access to the notes. So you'll have. I'm sure there are questions that are not being answered that people are too embarrassed to ask, but will be clarified by the notes. Yeah. Mm.
Or a simple announcement. Yeah, if you have everyone, if you have interest to have the method, please send your email to our secretary, and then he will send the electronic version to your email. Okay?
Yeah.
Yeah, Tingting's email address
There will be many emails to her, right?
is
That will be a lot of emails. Yeah. So homework.
yeah, okay.
Homework. That will be like the whole university may send email to her.
Yeah.
We didn't know there's too many emails.
I trust
Maybe
Tingting
announce
your way of
maybe put on a paper link.
Yeah, at least
Maybe we put on the some kind of web link and write the link on the board. Anyone can download. Otherwise, you can't get the
Yeah. I mean,
because
normally I would put this in a Dropbox and give an address, but we. Oh yeah, I have an idea. Why don't we post this on the WQC website?
on the website. People download.
Yeah,
Then
and then
we'll
people.
put the link on the board.
Yeah,
So only the people in the classroom.
yeah.
Otherwise, you'll get the common email.
okay.
Yeah, put on the link.
Okay. Let me show you since there are a lot of questions in this direction, I think it may be very clarifying to.
So Frank, the question today.
Yes.
Sorry after that. Now that you have a framework with
Yes.
classical variables and point variables,
Yes.
and the classical variables and point variables commute, then the question is, why treating them together at all if they don't do something severe?
Oh, well,
Respect to each other. Is there still room for something?
yes, let me show you. So the z's commute, but the d by dz's don't necessarily commute. That's where it comes. That's where things get interesting. So let's to address a lot of these questions about path integrals, about non-triviality, about formulating these theories. It's extremely helpful, I think, and we're ready to do it, to represent. Let's represent our classical theory in terms of something more familiar, that is, two quantum theories, which may seem much more complicated, but it is more familiar. And so we can bring all our knowledge of quantum mechanics to bear in understanding this unusual formulation of classical mechanics and the new possibilities it offers. So we start with an x and a p. Let's rename these as x1 and p2. And then we had to introduce lambda x and lambda p, which had non-trivial commutators with x and p, respectively. Let's call these p sub 1 and with a minus sign, it turns out, x sub 2. Okay. Now if we write down the standard quantum mechanical commutation relations for these guys, so the standard Heisenberg commutation relations they give us exactly, they're equal to the Koopman von Neumann commutation relations we needed to postulate between these guys to get our classical system. For the left-hand side. So the Heisenberg commutation relations for the right-hand side are exactly the same as the Koopman von Neumann commutation relations for the left-hand side. So we get to represent our classical system as two quantum mechanical systems in this way. Notice x and p are represented as x1 and p2, which commute with each other. So in this language, for instance, just to be concrete, our Schrödinger equation, recall, looked like our Liouville operator that we constructed looked like P over M lambda x hat minus u prime of x lambda p, like that. So it becomes